All right, so let's go through a few examples of analysis of activities and using this concept of static equilibrium and using what they call free body diagrams. And free body diagrams are basically stick figures to represent a situation. So if we have elbow flexion again, or the elbow joint, you have your external load acting down. We're going to call that R2. And then your external moment arm, called D2, from the center of rotation to that line of force. We also have the weight of the arm. So some people, during any exercise, also consider the weight of the arm times that smaller moment arm, because we represent the weight of the arm at the center of mass. And so both of these forces are pulling down and pulling your elbow joint into extension, so they are creating an extensor torque. Your muscle force, your biceps brachii, brachialis, is the force acting up. The perpendicular distance is the internal moment arm, and the muscle force is creating a flexor torque, right? And so the sum of the torques during a stationary equilibrium are zero. So muscle force times moment arm is basically, equal to R1 times D1 plus R2 times D2. All right, so let's look at a different exercise. You're doing basically a leg lift or a leg curl, right? So the flexor torque is equal to the extensor torque. So the weight of your leg is pulling you into extension, or if you have an ankle weight, and your knee flexor muscles are creating that flexor torque. So here's my beautiful free body diagram. This is supposed to be my thigh, lower limb, and my foot. And so the weight of the leg is acting down at a certain moment arm, and that's pulling you into extension, so creating an extensor torque. The force of the hamstrings acting at the moment arm for the hamstrings is pulling you into flexion. So the F of the hamstrings times the moment of the hamstrings is equal to the force of the leg times the moment arm, the external moment arm of the leg. And the center of rotation in this example is the knee. Here's a knee extension example. So you can see this is position 1, and this is position 2, so A and B, which has a higher torque. So basically the weight of your leg is acting down at a smaller moment in A. When your knee is fully extended, the weight of the leg has a larger external moment arm relative to the center of rotation of the knee, so it is creating a bigger flexor torque, and those are all resisted. That flexor torque is resisted by the muscle, the quadricep muscle times the internal moment arm, and the quadriceps create an extensor torque. And this is just good to know that, a good image to show that here's your center of rotation. This patella really increases the moment arm of your quadriceps muscle group. Here's one for your trapezius. So, in the clavicle, so the center of rotation is your sternoclavicular joint. Here I had the clavicle, the weight of the clavicle acting down, and then your upper trap acting upward or elevating that clavicle. But that's not really what happens with shrugs. You're not lifting the weight of your clavicle. You're actually lifting the weight of your arm. So in this case, the weight of your arm is acting down and pulling you into depression or downward rotation of the scapula, and your trapezius is elevating the scapula or upward rotation. And just note that the trapezius acts at an angle, so you have to resolve the vectors into what's the vertical component that's contributing to the elevation and what's the horizontal component that's working as a stabilizer. And here's another example. So here's your pelvis and your glute minimus, we'll say. And so the weight of your body is acting down and pulling you into a deduction. So this the body weight pulls down. You're standing on this limb, so this whole segment collapses into a deduction. Sorry about that. And that is countered by your gluteus minimus and medius, which is creating an abductor torque at a smaller moment arm from the center of rotation. And just to note that since the muscle is at an angle, only part of that muscle, the vertical component, is creating the abductor torque, or the rotation, and part of that muscle is creating a stabilizing force. And so then you could, if I give you this angle as 55 degrees, you could figure out how much is the vertical force of this muscle force, 400 newtons, and how much is in the horizontal direction. So again, go look at the resolution of vector videos. All right, here's a pretty simple example. This is the head. This is your hip joint, believe it or not, and this is your knee joint. And this is basically a leg extension machine, right? So here's the pad that you wrap around your ankle, and then you do extension exercises. So the weight acts down at a certain moment arm, and so that's pulling you into a knee flexion, and your quadriceps are pulling you into extension, which is why it is a quadricep exercise. Now, you could make this easier without decreasing the force. All you have to do is slide that pad, or where the weight is applied, further up your tibia, which decreases the external torque and makes this exercise easier. All right, so we talked about the patella, increasing the moment arm, right? So you can see it's a bad image, but there's a huge decrease in moment arm when you do not have a patella, and that decreases the external, or the extensor torque of your quadriceps, and actually you could not be able to walk without a patella. Another anatomical pulley, or a bony prominence that increases the moment arm, is your greater trochanter. It is greater, lots of muscles pulling on it, and so it extends these abductor muscles further away from the center of hip rotation, which increases the torque production. Some people are really strong with having huge muscles because they have very, very good moment arms. So here's an x-ray. You can see, let's say this is the center of rotation of your knee joint. Here's a lateral view, or a medial view of, here's your femur, your tibia, here's your patella. So the quadricep is attached at the tibial tuberosity, acting up. Here's the center of rotation, and this patella just increases this internal moment arm. Your calcaneus is another one that makes a huge moment arm for your Achilles tendon, which is attached to your gastrocnemius muscle. And another anatomical pulley is the bicipital groove, right? So it goes over the greater tubercle, pushes it out a little bit, so you have a mechanical advantage or an increased moment arm for that muscle. Anytime you increase the moment arm, you're going to increase torque production without having to expend more muscle force. And here's my cheap animation of the moment arm changing through the range of motion. So just so you know, the internal moment arm is not an anatomical point. It changes relative to the line of action of the muscle. And this is my version of a foot and a tibia. So this is your gastrocsoleus. And through dorsiflexion and plantar flexion, the moment arm between your gastroc muscle and the center of rotation of your ankle does change. So your internal moment arm changes throughout the range of motion. Here's if-then statements from the prep guide. So I'll leave you to go through those. And now here's another example. So you're picking up a soda. That's your external force times your external moment arm. The muscle force is your internal force times a much smaller moment arm. And this is just illustrating that your muscles have a mechanical disadvantage, right? Their moment arm is much smaller, so it has to generate much more force compared to this long external moment arm and a relatively small force. So if moment arm goes down, the force production requirements go up to maintain a constant torque. All right, and this is just for clarification. Torque is also called moment or moment of force, and is the tendency of a force to rotate an object about an axis, fulcrum, or pivot. So when we get into reading running and gait articles, which I think you're going to have to read one, their graphs are usually moment or moment of force, and by that they mean torque.